Greetings everyone, it's me Prathami and I am back with another video. In this video, we are going to explore about computer codes and the different types of codes. A computer code in general sense refers to a system of rules, usually an algorithm, that are used to represent information such as letter, word, sound, image or gesture in a format that can be understood and processed by a computer. Computer codes can take various forms depending on the context, such as programming languages, machine language instructions, data encoding schemes, and more. A process called encoding is used to convert information to computer understandable format and decoding to get back the information from the computer to human understandable format. Computer understands only one language and that is binary language, which uses only two symbols, ones and zeros. Such a code which is written using two symbol system to represent text, computer processor instructions or any other data is called binary code. To convert our information to computer understandable format, we have different encoding schemes known as the data encoding schemes. There are many, but we shall discuss the following: ASCII, ABCDIC, Unicode, BCD, and Gray code. We will discuss in this part ASCII, ABCDIC, and Unicode. BCD and Gray code will be discussed in the next video, that is part 2. Before you explore the different schemes, I request you to take a quick look into the fascinating history of the binary number system by clicking on the link below in the description. Now, if you're a first time learner, then you have a question: why so many encoding schemes? To understand this, let us very quickly throw light on the history of computer codes. It was during that time when the Babbage's difference engine was around. In 1837, International Morse code was the first one designed for telegraph system and not for computers. That is, in those days, encoding schemes were used for telecommunications. Morse code was developed by Samuel Morse to encode text characters as standardized sequences of two different signal durations called dots and dashes or dits and das. In 1870s, 5-bit Bordeaux code was also known as International Teleprinter Code, designed by Emile Bordeaux, was the first computer-like character encoding with control characters used for telex systems. In 1928, when tabulating machine and punch card system was around, IBM introduced a 6-bit BCD code capable of representing alphanumeric information. This code represents the numbers 0 to 9 by a single punch and uses multiple punches for uppercase letters and special characters. BCD here is also known as alphanumeric BCD, alphameric BCD, or BCD interchange code, or just BCDIC. In 1959, the US military defined its field data code, which was a 7-bit encoding system for use on military data communication lines. It became a US military standard in 1960. In 1950s, when the ENIAC and other computers were around, these different makes and models of computers could not communicate with one another. Each computer manufacturer represented alphabets, numerals, and other characters in their own way, mostly BCD and others. Remember, when I say BCD here, I refer to BCD for character encoding or BCDIC and not BCD for numeric code representation. So, in 1961, Bob Bemer of IBM submitted proposal to the American National Standards Institute, that is NC, for a common computer code. Bob Bemer is also known as Robert William Bemer. He is a computer scientist and an IBM engineer. He is sometimes also known as the father of ASCII because he introduced the escape sequence character, backslash, and curly braces characters. In 1963, ASCII was approved as American standard, but was not successful widely because IBM chose to use ASCII code. In 1950s and 60s, International Business Machines, so called IBM, did so extremely well, and also in 70s it was the only company in business. Also, IBM was the first to enter into business and to build the trust and long-standing relationship with the customers of government and industry. Even in the NASA's Apollo missions, IBM computers were used. There were other players in the emerging IT industry, but in terms of market share and revenues, they faded in comparison to Big Blue. Well, that's what they nicknamed IBM. ASCII was originally developed for teleprinters or teletypewriters. ASCII uses 7-bit binary code, so it can represent 128 characters. Digital computers used 8-bit binary code. Since it can represent only 128 characters, other characters such as cent could not be represented in ASCII. A cent is, as you know, a monetary unit of many national currencies that equals 100 of the basic monetary unit. Extended binary coded decimal interchange code or ABCDIC is an enhancement of binary coded decimal, that is BCD, an oldest encoding scheme. ABCDIC was devised in the same year as ASCII, that is 1963, by IBM. Since ABCDIC was 8-bit code, it would support 256 characters, which is twice the number of characters supported by ASCII. This means that ABCDIC could represent more characters than ASCII. Hence, ABCDIC was the first choice for IBM. Also, IBM machines were in high demand in those days, so company did not want to spend time in redoing the software changes for ASCII peripherals such as card punch machines to ship with its System 360 computers. So the company settled on ABCDIC, and yet IBM was a chief proponent of the ASCII. ABCDIC was best for punch cards used by IBM machines, but they were becoming less popular because of the following issues. Sorting in ABCDIC put lowercase letters before uppercase letters and letters before numbers, but same worked very well in ASCII. Curly braces, which would be used in C programming, that did not exist in ABCDIC, making translation to ABCDIC systems difficult, but that existed in ASCII and had no issues. On March 11, 1968, US President Lyndon B. Johnson mandated that all computers purchased by United States federal government support ASCII, thus solidifying ASCII's place in the American IT industry. Consequently, ASCII underwent improvisation and was revised for years and finally came up with extended ASCII that used 8-bit code which consisted of 7 information bits and 1 parity bit used for error checking or for representing special symbol. So, in 1981, extended ASCII was introduced by IBM and was used in its personal computers and soon became the industry standard. Extended ASCII can represent 256 characters, which include special characters as well as characters from other language. For some countries, 8-bit extensions of ASCII were developed that included support for characters used in local languages. For example, Indian Standard Code for Information Interchange for India, that is ISCI. Even some of the manufacturers developed their 8-bit extensions of ASCII to include additional characters such as box drawing characters, semi-graphics, and video game sprites, where additional language was not needed. A sprite is a term commonly used in computer graphics and gaming to refer to a two-dimensional image or animation that is integrated into a larger scene or game environment. Coming back to our topic, so eventually, ASCII helped standardize computer text a lot and was widely popular on internet. However, even extended ASCII did not include enough combinations to support all written languages. Asian languages, for instance, require 1000s of characters. This limitation gave rise to a new encoding standard, Unicode, and UCS, Universal Coded Character Set, that support all written languages of the world. Because it incorporates ASCII as its first 128 code combination, Unicode, especially UTF-8, is backwards compatible with ASCII while also representing many characters that ASCII cannot. Now let us understand about Unicode. Unicode is an international character encoding system designed to support the electronic interchange, processing, and display of the written text of the diverse languages of the modern and classical world. It includes all the letters of the word as well as emojis and other symbols using a uniform encoding scheme. The Unicode standard itself defines three encoding schemes: UTF-8, UTF-16, and UTF-32. The expansion of UTF is Unicode Transformation Format. UTF-8 is a variable length encoding and takes 1 to 4 bytes depending upon code point. Here, smallest binary representation of a character is 1 byte. Here you can see the UTF-8 conversion table with the code point. The X characters are replaced by the bits of the code point. Unicode code point is written as capital U plus the hex value of that code point. Example, U plus 0041 is A, capital letter A. U plus 0906 is A, that is in Devanagari language. Since UTF-8 is variable length encoding, it gives us ability to transmit in a single byte, 2 bytes, 3 bytes and 4 bytes. And it does this by using the preceding or the most significant digit of these ones and zeros to identify whether we are receiving 1, 2, 3 or 4 bytes. If we look at the bunch of zeros and ones in memory, how do we identify whether we have received 1, 2, 3 or 4 bytes of information? Well, all the UTF-8 1 bytes starts with a 0 as the MSB. The remaining 7 bits are plain 7-bit ASCII and not the 8-bit extended ASCII. Extended ASCII is no more used now. UTF-8 is the most widely used encoding system due to its backwards compatibility with ASCII. Backwards compatibility means if something is stored in ASCII, it can be read in UTF-8. So, if the MSB is 0, then we know that it is the first byte. We can encode U plus 0041 in UTF-8 1 byte like this. MSB starts with a 0 and remaining 7 bits contain 1000001. That is by applying hex to binary conversion we have got this. So with 7 bits, the range of characters we can represent in UTF-8 1 byte is 0 to 127. That is 0 to 1111111 in binary and 0 to 7F in hex. For UTF-8 2 bytes, it has to start with a 1 in order to distinguish it from UTF-8 1 byte. So, UTF-8 2 bytes starts with MSB 110 and the following or the trailing bytes will start with the MSB 10. And this also applies for trailing bytes of 3 and 4 bytes UTF-8. Now, if you open up memory and come across this byte starting with 110, then you know that it is the first byte of a 2-byte sequence. And if you come across 10 in the MSB of byte, then you should understand that it is not the first byte because there must be another byte that came before that identifies the number of bytes we expect to receive. So, the MSB of the first byte UTF-8 is 110 and the MSB of the second byte UTF-8 is 10. Hence, with the remaining 11 bits, the range of characters we can represent in UTF-8 2 bytes is 128 to 2047. UTF-8 2 bytes represents the code point for almost all Latin script alphabets as well as combining diacritical marks. For UTF-8 3 bytes, the MSB of the first byte starts with 1110 and the MSB of the trailing bytes, that is second and the third bytes, start with 10. So, with the remaining 16 bits, the range of characters we can represent in UTF-8 3 bytes is 2048 to 65,535. UTF-8 3 bytes represents code points that includes most Chinese, Japanese and Korean characters. And for UTF-8 4 bytes encoding, the MSB of the first byte starts with 11110 and the MSB of the trailing bytes, that is second, third and fourth byte, starts with 10. So, with the remaining 21 bits, the range of characters we can represent in UTF-8 4 bytes is 65,536 to 1,114,111, and the code points include emoji and mathematical symbols. So, to represent 5 bytes, the MSB of the first byte has to be 111110 and the MSB of the trailing bytes as 10. And in this way, the expansion is easy with Unicode system. UTF-16 is also variable length character encoding, but either takes 2 or 4 bytes. Here, the smallest binary representation of a character is 2 bytes. UTF-16 is used in Microsoft Windows API, Java programming language, JavaScript, where minimum byte requirement is 2, that is 16 bits. By the way, fixed length UTF-16 is called as UCS2, which is not used nowadays. On the other hand, UTF-32 is fixed 4 bytes. The main use of UTF-32 is in the internal APIs where the data is single code points or glyphs rather than strings of characters. A glyph is the specific shape, design or representation of a character. API is Application Programming Interface. The main advantage of UTF-32 is that the Unicode code points are directly indexed. Finding the nth code point in a sequence of code points is a constant time operation. In contrast, a variable length code requires linear time to count n code points from the start of the string. So imagine if you want to store the string hello world, how much space would be taken? Here are some binary representation of bytes. If it uses UTF-8, it would take 11 bytes in memory. If it uses UTF-16, it would take 22 bytes in memory. And if it uses UTF-32, it would take 44 bytes in memory. So from this you can see UTF-32 is not space efficient. So it is very rarely used, mostly used only in APIs. And that's it with the part 1. We shall discuss about BCD, that is numeric encoding and gray code, in the upcoming video, part 2. So stay tuned. Thanks for watching and don't forget to like and subscribe.